software engineer. There has been a lot of talk today whether you're a data scientist or you're a software guy. I'm a pure software person, Linux kernel for the last like 6, 7 years. Why I'm here is that I joined Samsung around a year ago, working on enabling of new ecosystems on open source projects, including Linux kernel, and one of the projects that I'm taking care of or working on with different other teams is something that we're calling computational storage, or that the industry is now calling computational storage. What I want to talk to you today is, how we got here, what is computational storage, and how it might be relevant for you, that you're the experts on all the machine learning, data analytics, and which I don't have much idea about. So I want to start a little bit from the scratch. What is solid-state drives with computational storage? How we got here? Something that's called NVMe Express. Have any of you heard about NVMe in the past? Yes, you know a little bit about it. Well, I'll cover what it is and how it's a little bit relevant for the topic today. I'm gonna talk a little bit of before we got to this computational storage. There has been like decades of research, something called near storage processing, on about how to accelerate computation near to where the data is stored, that locality. And we're gonna get into this computational storage. It's the new buzzword out there, which is basically number of companies getting together and try to standardize how you talk to these devices that can do computation near to the storage. And then we're going to cover a little bit about the ecosystem and a particular architecture that we're working on. So NVMe Express is non-volatile memory express, is the new kid in the block for storage protocols. We've been working on that for around 10 years. It is relevant because we come from a world that traditionally has been spinning Rust, hard drives, milliseconds, 6 times. Interface was based on a single queue, based on a probably single processor, single core, very slow storage. Suddenly we get flash. And then flash, we're moving for these millisecond latencies to microsecond latencies. It's been like 5, 6 years since we have 70, 80 microsecond latency for reads on these devices. And low latency devices and new memory technologies today, we're getting to these 10, 15 microseconds. So we need a new interface that is scalable, that is high throughput, that can take advantage of multiple processors. This is very relevant because we cannot scale vertically anymore in number of CPUs. You might have realized that we're not getting more gigahertz. We cannot feed more computation on that because physics will make the core melt. So we are growing horizontally, basically putting a lot of cores and then trying to get advantage of doing things massively parallel. But if your device cannot, take on that, then it's kind of useless. So NVMe is about, at the end of the day, taking all the use out of flash and putting it together into highly parallel multi-core architectures. We'll see how this is very relevant for today data cloud infrastructures. Cool thing about NVMe is that it's designed from the ground up. It started being PCIe based. PCIe is basically the interconnect that is on all your devices. The connection to the CPU. It's kind of a bridge that is a bus, but it can work on any other type of fabric. So you can do something called RDMA, or you can even do TCP/IP. Cool thing is that your CPU doesn't care about it. You're just going on the other side of the fabric. You might see a little bit more of latency, but you can basically disaggregate your application on several storage nodes, and that that follows the view of massively doing things massively parallel, which is pretty good. One important thing is that we have very awesome support in Linux. So if you look back in the days to NVMe, this became relevant. There was this startup, super awesome startup called Fusion.io. Maybe you've heard of it. It was the first ones that put flash on a PCIe interface. They basically revolutionized the market. They got acquired by SanDisk for $1 billion, then by Western Digital, etc. The problem was that they created a driver for a particular device put on a PCIe slot. Then other people like Intel, Samsung came and said, I want to do the same thing, but then you need to develop your own driver. And people that maybe have developed drivers in Linux or any other operating system, they know it's hard. And then we all run it on your crappy driver, which you might not maintain anymore. When we put in Linux, we have a bunch of very good engineers working on this cross-industry. It doesn't matter where you walk. So this is pretty good. And the last thing that I want to say about NVMe, which will also become very relevant for this particular presentation is that NVMe at the end of the day is a transport. It was designed for storage, but it's not specific about storage. It's basically 64 bytes with a submission and completion queue. You just put a bunch of them, you ring a doorbell, and then your device consumes it, puts it on the completion queue, comes back. And again, I'm going to come back to this because it's relevant. If you do not think you should care about NVMe, so in 2019, we're shipping more NVMe devices than SAS and SATA. This is the first year that this is happening. Partially because data centers, they've qualified already. This is stable, it's fast. They've gone through this 3-year project, process where they need to modify their whole infrastructure. So it's kind of a tested thing, and from here on, it's just going to take off. So I don't think that we're going to see SATA SAS disappear in the next 5-10 years, but eventually they will just fan out, and then we're only going to see NVMe because it's cheaper. Well, it's around 2 to 2.5x with SATA and SAS, but prices are dropping, so it's becoming cheaper and cheaper to adopt, and this is also important. So now you know a little bit more about NVMe. What is near storage processing? So the idea is pretty simple. It's basically you move compute to where your storage is, or where your data is. So the way we compute data today on a typical von Neumann architecture is that you go to your storage device, you pull all the data out of your storage device. Here I'm putting a little bit more complex. You might have some PCIe on your storage node if you're running on your Amazon or Azure or whatever you're running on. Going through the fabric, you move into some sort of CPU root complex. Then you're computing all the data that you need, and then you are maybe storing some results back. This is good. It works. It works very well when you have enough storage locally to move it kind of fast, and then when you might not have much data. On the people at Samsung that are working on this, we have customers that already have a data lake with 1 exabyte. So that's not like crazy numbers, and it's just going to go up and up from there, and it's partly your fault. So it's just going to get more and more. When you start moving, we're bounded by how we submit, how we talk to the devices. And the way we talk to storage devices is through IOs. So it's input-output, right? So you have all this data that you compact on your data structures that are kind of complex, and then they're optimized for you to compute in place, in memory, and all that. But then we transform it into these logical blocks that are like 512 bytes to 4 kilobytes, and then we need to read all of them back. So if you have a very rich data structure that it goes across 1 megabyte, we're going to partition that. And it doesn't matter how rich your data structure is. When you talk about near storage compute, you change a little bit the paradigm, and then you say, instead of talking this kind of I/O and then trying to move all the data, I'm going to have a kind of a query, if you want to think of it in these terms. So I can ask the device, hey, can you do this for me? And the device will locally try to answer that question and then put the data back. The important thing here is that you're not limited by the density of the data. You're limited by the density of your query. So if your query, you have like, to put an example, 1 exabyte of data, and then you want to say, hey, give me the oldest guy in all this data set, then basically your query maybe has like a table or a row or something that is a few kilobytes. You don't need to move all the exabyte down to the CPU to compute this. And I'm going to put a little bit a quantified example of this in a couple of slides. The challenges with this is that in order to do this, you need new interfaces. There are hundreds of these interfaces through time. There are 0 that are standardized today because this is a very hard time. Block devices have been here for decades, and they're here at the store. So adoption and standardization is a big thing, but we don't have any today. With people that are in storage industry, when you talk to them about this computational storage, they say, "Oh, we invented that, last week." It's not true. This is something that has been done for decades in the past. Actually, the first reference I could find goes back to the 50s, but it's more about in-memory processing, so it's not really persistent. I'm not going to put it there. First, really computational near storage processing I can find is around before the 70s, I think it's 68. The slides are available, so you can just go and read some of the papers. The thing that I want to point you to here that is important is when people started talking about, we need to move some computation down to the device, the fastest supercomputer in the world could do around 22 gigaflops. We could do around 10 megabytes per second, and storage could do like 5 megabytes per second, and it was around 1 gigabyte at all, right? And this is interesting because I have a good friend that calls this the biorhythms of computer architecture. That is basically you have a storage, compute, and networking, and how you design your systems is very much based on where those technologies are moving at the time. One time networking is can provide you more than you need. Sometimes it's going down. Then you change all that. But today, we're in a world where, if you look at the last AMD processors from Epic Run, you can do 2 teraflops on a single chip. They're super expensive. If you don't want to go for price, you can move to your RISC-V architecture. You don't need to pay any royalties. It's around less than 1 gigaflop, but it's super, super cheap. So you can put a lot of them in parallel. Networking with master 100 gigabits per second. You can find some people doing 400 gigabits per second. It's not still very much deployed, but it's there. And storage, something that you can buy on Amazon today can do like 32 gigabits per second. We're talking about tens of terabytes. People, when this CAFS paper, the content addressable file storage, came out, there was another paper right there in the 670s that they basically were saying, we don't need to do this anymore because we have enough compute. So we can just throw your data to your CPU. Today we're in 2019. We storage kernel people, we count cycles. So if you spend one more cycle than necessary moving your I/O, people complain because this translates into millions for data centers. We'll see, this is how a normal architecture looks today. We call it, the buzzword is composable disaggregator infrastructure. Basically means you don't have racks on your data center anymore where you have a lot of CPUs and then you have a lot of storage and then you have some networking because that doesn't scale. You normally need a little bit of computing for some applications, but a lot of storage, and some others you need a lot of compute, a little bit of storage. So people disaggregate. So you have a lot of compute nodes that scale horizontally, and then you have a lot of storage nodes that also go horizontally. If you go, for example, to you run on AWS, you have like this new Nitro virtual machine that can spin a machine in less than a second. So if you need more compute, they can just put it out there for you. They don't need to pay more, to have like dual processors, or they need to buy new racks to do this. They just have it completely disaggregated. So, in an example on why this is, and obviously they make you pay for what you use, right? So part of the trick here is that they don't need to overscale everything for when you have your Black Friday. They have all this and they want to utilize it, maximally utilize it. So if you're running cycles in running your storage, you're paying per the cycles that you're using. So you're actually paying them money just to move your data around. And you don't want to do that. You want to pay the money for the time that your application is running on this cloud infrastructure. So take an example of data lake that you can use for analytics. So on a typical storage node today, you have like these 100 gigabits per second. Let's take that as an example. If you use like traditional SSDs, you have 2 connectors. They do like 3-point-something gigabytes per second. It's around 24 gigabits per second. That means that you have around 500, a little bit less than 600 gigabits per second on a 300 terabyte storage rack. That means that for 1 exabyte, you need around 3,500 of these. Let's say that you want to compute something on that. How much time does it take you to take that exabyte out of the storage nodes, providing that you don't do anything else? It's around 7 hours. If you start doing the lightest computation of these things, you're putting 10x, 100x on this. So and this is how you're doing this today, by the way. You probably don't think about it because you're used to run your query and say, it's going to take me a couple of weeks, or maybe I'm running on a subset and then I do silos or whatever. But at the end of the day, this is what's happening. And the question you should ask yourselves is, how much data are you throwing away on the first order filtering that you're applying? So probably it's like 90%. It's more than 90%. A lot of customers that we have, put this in a 95+%. And this is, at the end of the day, you're spending CPU cycles basically for nothing. So this is bad from a performance perspective, from a power perspective, basically for any metric that you can think of. Trying to make the same point again. Now, looking how it looks on a particular storage node. If you're running on modern architecture, you can say, oh, I'm not using CPUs to run my stuff. I'm using GPUs or I'm using FPGAs. Well, it's the same problem. Your storage doesn't talk to those FPGAs or GPUs. You're basically using a CPU to move data around. So maybe your CPU is not your central processing unit, but it's kind of your control plane unit, just moving data back and forth. But you're still, moving data takes a lot of cycles. So if you look on your left-hand side, you can see you can put that accelerator many places, different cloud providers, or if you're running enterprise yourself, put it in different places. You can put it next to your CPU. You can put it on the same PCIe lane as your CPU, as your storage. You can even put it embedded on the CPU, like QTA technology or other things that people are doing. But at the end of the day, you're moving data. So you're just scaling based on you're kind of a loop saying, OK, for the number of IOs that I have, move here and compute. What we're trying to put here, I'm using two examples. One is you can put the accelerator directly on the SSD. This is one option that allows you to scale within the SSD in itself, but it might not be enough because SSDs, even though they're growing, especially with more bits per cell, pretty easily we can get in 1-2 years to 64 terabytes on a single SSD, maybe 128 terabytes compared to the amount of data you guys have. That's not enough. Another option is maybe putting the accelerators on the same PCIe node as your SSDs are running so that you can move data and then compute within the storage node itself. So you're still moving data, but not that much. The cool thing about this architecture that I like very much is that data locality is king. So this forces people thinking about putting data that belongs together, going together so that you can compute it at the same time instead of just putting things all over the place. Computational storage. So we've come a long way from this near storage processing called ActiveSys in the past. Now computational storage. What's different from for the computational storage perspective is that there's a lot of companies that are behind this. It's not only Samsung, it's not only Intel, it's not only a bunch of startups. I think last time I checked for this, there's something called SNIA that is storage networking. I don't know. It's like industry. Something, it's kind of a standards body that brings a lot of companies together. And we're all working together towards standardizing it because we realize the same problem that people that have been working on this for years found out, and it's that if you're trying to propose a new interface and not everybody uses the same interface, then this is not going to take off. It doesn't matter how big your company is. Doesn't matter. Samsung, I think we ship like around 35% of all the SSDs in the world, but it doesn't really matter. Any data center today needs at least 2-3 sources. So if it is not the same interface, it's not going to work. On the standardization group, we're focusing on the modeling itself, not that much on a single solution. This is because many different, especially startups, are working on very specific use cases. So there are people, as I mentioned, that they want to put compute without storage, but it's on the same PCIe lane. This is important because, again, you're moving data, probably something that we call peer-to-peer, basically that you don't need any CPU going to tell you what the data is. You're basically telling your accelerator, hey, can you go pick up the data from the SSD? And they can talk together without consuming CPU cycles. This is actually pretty cool. Other people, like Samsung in this case, were building SSDs that come with storage in them. This targets different use cases. And then we have something we call computational storage array. That is basically a way to combine these on the same architecture. So it's kind of like a meta architecture more than a solution itself. From Samsung, and I'm going to talk about what I know. That is Samsung that we call it a SmartSSD, but this can apply for other people are building these products too. And what is important is that it's not that much about what the product is in itself; it's about what it's enabling. So you have plenty to choose from. So this is in particular a computational storage drive. It looks basically like you have an FPGA, and then you have a NVMe controller. So if you're used to work with FPGAs, basically from your host, you're going to see Three physical functions. You're going to see an NVMe controller coming up, you're going to see your FPGA coming up, and then you're going to see a bunch of DRAM. And then you can program this the way you want. I mentioned a little bit of that before. We have something that we call internal peer-to-peer path. This basically means that when you want to move data from your FPGA to your NVMe controller or the other way around, no CPU is involved. Meaning that if you're asking a complex question that needs to put 1 terabyte out of the SSD, you're not moving that terabyte all the way through your fabric, PCIe, blah blah, coming back. You're just doing it internally, and yes, physics, if you're closer, is faster, right? And the bandwidth of these PCI lanes is just much larger than the PCI lanes that you have exposed close to your CPU root complex. Different teams are doing different projects, and I don't particularly like talking about, for this particular financial architecture, we got like 3.5x or 17x or whatever x, because it depends on the workload. To me, from an architecture perspective, what is very interesting is how do you scale with the number of devices? And then you can see that with this type of architecture, you can scale almost linearly. You have one device, you gain the first x, but then as you put a different device, you put close to 2x, a different device, close to 2x. And this is just because you can run all this in a massively parallelized world. If your data is local within the SSD, you've done that work, then you can run a query parallel on all these devices, run your first, second order filtering, then aggregate, and then you scale linearly. This is actually pretty cool. However, it doesn't matter how cool the architecture and the device is in itself, we still have a huge programming gap. When I talk to our firmware hardware guys, I'm like, up here. You work on the host, you work on Linux. And probably, if I talk to most of you, I'm like, all the way down here. We have different expectations about how things work because you think of it on your domain-specific languages, on your very dense programming languages. To me, the world looks like C and Bash every now and then. And to you probably speak protocol buffers or Parquet. You don't care about what's happening underneath. So one of the main challenges we have from an open source perspective is how can we make sure that we enable people like you on an architecture that changes so many things, like here. And I think that we have two ways of doing that, and that's what we're targeting now. On your left side, there's something that we call acceleration platform, and then on the right side, we call NVMe Computational Storage Platform. I'm going to start with the acceleration platform. So the acceleration platform is basically, is under the assumption that if you do care about accelerating and you have the capacity, then you're going to have people that know how to do the work. So, we basically sell you either directly to you or through a cloud vendor with some instances, a bunch of these devices that gives you an FPGA, a CPU, and then, if we made a compelling case, then you're going to use it instead of putting an FPGA or GPU in the side because you're going to save money. You can either go and bring your own IP. So if you're used to use FPGAs, then you just put your IP there, and then it's not very complicated. This is a Xilinx FPGA. So if you're used to do SDXL or OpenCL or something like that, you can get it started very quickly. If you do not, you don't know that much about the internals of an FPGA, you can also come and put some services on top of that. This particular here, I think, is not very relevant for you. This is more about traditional storage services. It's about doing compression and decompression and compaction, deduplication. This is important if I run a data center because I can sell you 4 terabytes and only have 2 because I just compress the data. But for you, what's important is that, if I put it on the application side, then you basically can have like some connector for your framework, and then you run Parquet. You go through an accelerated framework, and then you don't care what it's running. Your query, how it's going through the stack is just you just see that it's go faster. We have a lot of experience working with different customers here, and you're very welcome to come talk to me, and then I can put you. I don't do much on this side because I'm more like a operating system guy, but I can put you in contact with the people that works on the acceleration frameworks here. And there's a lot of customers that have done demos and stuff. You're familiar with people like BigStream using these devices to accelerate Spark and Hadoop and things like that. Another way of looking at this, and this is somewhere where I'm more interested in, is, well, what if instead of looking at this as two separate devices that happen to be connected within the same device, we look at it from a perspective where the same SSD speaks a number of accelerations. And this is where it becomes important. Remember, NVMe is a transport. So it's not that much about me telling you, hey, read or write. That is where NVMe does a lot today. I can use my 64 bytes to tell you, can you find a mail over 35 on this dataset because I know that it has this particular structure? Or can you run a query because I have offloaded my database engine so it speaks, like SQL or whatever non-structured key value, RocksDB, whatever you want to do down there because I offloaded my database engine. What is cool about this is that the changes we need to do on the operating system level are actually not that much because we already have a very high performance storage stack and a very good common NVMe driver. So we can just extend the NVMe driver to understand these commands, expose us all the way down to the application. It's work, but it's not a manageable type of work. And then we already have a number of user space libraries that deal with these non-block interfaces that can make your life easier. And then you can run the same applications. At the end of the day, you don't care how this is going. The cool thing is that you can just run this on any cloud server, and then really you do not care whether your cloud provider is putting these SmartSSDs with FPGA, or they've done, other companies have come and put an ASIC or a EPU or something like that. So it enables you to go cross-vendor and at the same time get all the benefits. And obviously, at Samsung we will compete at the device level. Oh, I have it here. So I only have 2 slides left. From a standardization and open source perspective, we're working on making this available through the SNIA that I mentioned before. There's a technical working group called Computational Storage. Attending the meetings, you need to be a member, but it's free to be a member. It goes on revenue of the company, so a lot of startups can come in from free if you want to join. A lot of the work is also done in the public, so you can visit that website. We're at the point where all the work that we've done, we're probably trying to merge it with the NVMe standards group. So basically, we already have support for something that is called different namespace types. It's basically you can speak block storage, but you can also speak all the things, like key value or something that we call zone namespaces. Unlike this, you can do computational storage, so that you can basically put an SSD and then you ask your SSD, hey, what can you do? What type of acceleration do you support? And the SSD answers you, and then you can send commands towards this interface. From a Linux open source perspective, we have very good support for NVMe, and that includes NVMe over Fabric, so you can run this on any fabric that you can think of today. There is support for the acceleration platform model. On Xilinx has put good tools like SDXL. There's also non-Xilinx specific like OpenCL, and there are many others for programming your CPU. There are a lot of research and FPGA just-in-time compilers, things like that. At the end, there's a good ecosystem. And when we start merging this into NVMe, we will go and do the work in putting this on the NVMe driver in Linux. So I hope this made sense to any of you, but if it didn't up until now, I just have like 3 takeaways. First of all, if you're running on a modern infrastructure, accelerators are in that infrastructure. They're important. They are used for domain-specific workloads. If you don't use them themselves, you should, because they can accelerate, and then it's actually cheaper than anything else. When you start thinking of accelerating platforms that put together computation and storage, they actually solve today's real life problems. We have a number of customers that see a lot of benefits in terms of this power reduction, data movement reduction, cost reduction, just moving the stack to this new architecture without doing many changes. If you actually go and optimize for these type of architectures, you can have a lot of benefits. And then, there are many solutions down there. Samsung is pushing for this SmartSSD, which we're shipping to different particular customers, and it's probably become available for the general public in 2020. So if you have any questions, you're very welcome to contact me or drop an email. Thank Thank you very much.